Hello everyone, today is our third module of IMAT Mathematics. We're going to study second chapter which is about functions. Since IMAT requires rapid problem solving and conceptual clarity and you don't get to use a calculator, so we're going to focus on some shortcuts and some examples that's going to make it easy for you to solve the questions. First of all, let's take a look at functions. What is a function? Think of function as a vending machine, an unforgiving vending machine. When you press a button, let that button be input X. When you press that button, you must get exactly one specific output or item. Let the item be shown as output Y. That's how when you press a single button, you get exactly one button. That's how a function is worked upon. Similarly, if you press a button A and it gives you both chips and soda, if you press a button A and you get chips and a soda, then it means that you're getting two output at the same time, and it's not on the definition of function. So it means that the machine is broken and this is not a function. It doesn't give you a function. But if you press two buttons at the same time, it can lead to a single snack or single item or a single output. It is still in the definition of function. Now let's take a look at the define of a function. A function from set A to B is a rule that assigns to each element X in A exactly one element, such as we had a one output and a one input is the same as this. So the keyword here is exactly one. So you have to get a single output no matter how much or how many input you put inside it. Now we have some parts of a function. First is the domain. A domain is a set of all valid input values, X values. Here in the example of a function, here I made a graph of function. Here 1, 2, 3 are the inputs which are in the domain of a function. This here is the domain of a function, and every domain must produce exactly one output, as I told before that there must be one output. Next is codomain. Codomain is the target where the function or the values of the domain must hit. Here the target of the function of the domain of the function is codomain, or this area here. Next is range. Range is actually the answer of the domain. When you put a domain in a function, when you apply domain in function, the answer or the result you get from it is actually the range of it, range of that specific function. Now there is notation. The notation of a function is f of x. X can be changed with other variables since x is independent variable here, so we always or mostly use x. Then there are types of function. We're going to study it in our further slide. There are basically two types of function. One is 1 and the other is on 2. So a function where a single output produces a single input produces a single output is called 1, 1. Says that here when 1 lands on A, it will produce an image which is A, 2 lands on B and 3 lands on C. But no two distinct elements in the same domain ever point to the same element in codomain. Like if I move it like this, then this is not a function or not a 1-1 function anymore. So a single output must fall on a single input which is distinct. So the formula here is, if you say that the function A and the function B are equal to each other, then their images are basically the elements of codomain that make a pair with the output, the input of domain. Like if I hit 1 with A, then A basically becomes an image. So here A and B are the images of the function. In the last slide, we also said that range is also sometimes called image. So if the function are equal to each other, then their images must be equal to each other too. This is the condition for 1-1 function. Now we are on to the next function, which is onto. Now in onto function, the condition is that the elements in codomain must get hit by at least one function, by at least one element from the input codomain. Like here I have two elements in the codomain and they must get hit by at least once. Since the output, the input of the function must not get left out, so I have to hit 3 onto B twice. For 1-1, this should not be in the condition of the function, but in onto this is considered okay. So basically the codomain is completely dominated by the domain. So it means that codomain here gives all the answers of a function. So codomain is equal to the range of the function. Onto the condition for onto is codomain is completely equal to the range of the function. Sometimes we say that there is an element or an image that exists in the function which is completely equal to the function. It's some kind of a difficult concept, so we're going to stay on codomain equal to range thing. Next we have vertical line test. It basically tells you when a function, when an equation is a function or not. So when you graph a function, if it intersects the x and y axis of the coordinate plane at a single point, then it is a function, but if it crosses it twice, then it's not a function anymore. Like if I draw a line like this, it intersects x-axis at a single point here. But if I drew another straight line, but it ends up crossing or intersecting x and y axis at the same time, then it's not a function. Similarly, if I draw a circle, if the circle intersects 2 points at the same time, then it represents it's not a function. So if you get MCQs about whether a circle is a function or not, you can without hesitation tell them that's not a function. Next we have how to find a domain and range of a function. So IMAT questions basically love to hide domain restriction, so you have to immediately know these 3 red flags. The first one is your denominator. If the function is in the form of fraction, your denominator must not be 0. like if there is something under the fraction line, whether it's 1 or not above the fraction line, if there's something below it, then that something must not be 0. Basically, it creates an infinity or makes the function undefined. Since we know that anything below 0 is equal to infinity or undefined, it creates a math error. Next we have the even roots. The even roots must be positive or they cannot have negatives. Since we know that square roots or even roots produces an iota or a complex value which cannot be solved without using complex analysis processes, so that's why if we have a function that has a negative under the square root or an even root, then that must not be considered a function or its domain cannot be found out unless until we eliminate that factor from the function. So anything under the square root or an even root must not be 0, since that creates a complex number. The last one is the logarithms are strictly positive. The logarithmic values must be positive or cannot be negative. It's the same as we studied for the roots. So logarithm and a negative sign with a negative sign produces math error. It cannot be solved further. So log with a value of which is something, and that something must be positive. Now we have an example where we have to find a domain of function. First of all, we have to eliminate the factor which can cause a negative under the square root and a 0 under the fraction or on the denominator of the function. So to eliminate that, first step is root. To find that the root must be equal to or greater than 0, we can solve it by taking -2 on the other side of the question. Here the function will be we will find the domain of the function if x in the function is greater or equal to 2. Our second step is the value in the denominator must not be equal to 0. So when I place -5 on the other side of the question, then it will become positive. Now the function will give the domain when the x is not equal to 5. So x is greater than equal to 2 and x is not equal to 5. Those are the two conditions, that restrictions that are put on x to give a domain of the function. So the combined domain from those two steps is, to combine a domain we basically use union, since we are dealing with intervals instead of whole numbers, natural numbers. We are dealing with intervals, and there are infinite many numbers inside those tiny small brackets. So we're starting with +2 and goes up to 5. I'm going to apply an open bracket here. Open bracket here denotes that 5 is not included in the set. Since x is strictly not equal to 5, so anything above and below it is fine. So I'm putting an open bracket. It denotes that anything other than 5 is included in the function. Now union to this is the the negative side of the real line, and we're going to the positive side of the real line. Since x is supposed to be greater and equal to 2, from 2 we can apply it all the way till the positive infinity of the question or the real line. On the infinity, negative or positive, we always apply an open bracket. You can know the reason, since it's not a number and we cannot include it in our interval. Since we are about to graph the functions, you must know that a function can be transformed by slightly changing its equation. To know that how it is changed without the need to graph it, you have to learn these shortcuts. The first is here. I'll show you how that transformation actually works. Here are a few graphs for y is equal to x. For a function y is equal to x, the graph is going to look something like this. But if I add a positive 1 in the function, then it will make my graph to go a bit higher, like this. So graph basically shifts from a slightly tilted point by increasing or modifying the equation by 1. Similarly, if I have y is equal to x, which is basically a straight line, if I modified it by changing the equation and decreasing it by 1, then the graph will slightly decrease by a single point. That's how we're going to study all the other changes in the equation of the function. Let's take a glance on the graph here. That's all about the shortcuts. When the function has a scalar increased in the equation, like we just studied in our example here, y is equal to x. When the function has a scalar increase, it doesn't matter how much, so the graph will shift up to k times. Like when there was a 1 increase, the graph shifted 1 times above and 1 times below. That's how if there is k, then the graph will shift up. Then if there is negative k, the graph will shift down. And if there is change in the dependent value, dependent here is x. So if there is a change, negative change in the value of x, the graph will shift to the right. And if there is a positive change in the dependent value, which is x, the graph will shift to the left. Then there is stretch means it will take more space in the coordinate plane, but if we multiply it by scalar quantity, the graph will compress if you multiply with a scalar quantity which is a negative quantity, and the graph will reflect itself like in a mirror. If we apply a negative sign with the whole function, and it will reflect itself like in a mirror, but like from left to right. If we apply a negative sign inside the function with the dependent value. Let's take a look at some examples. Here's a graph of y is equal to x squared. Make sure you know that a linear equation like the one where x has a degree of 1, it will give a line in a graph. But a quadratic equation where the degree of x is 2, then the function will draw a parabola like this shown in the screen. We're going to apply some shifts on the function that are being drawn here. according to the table we studied below. Let's apply a shift here. We're going to add 1 in the parabola. It will go single unit up from its original place. Let's draw it like that. It won't be stretching, and it will just go up. Similarly, if we decrease a single point, it will go a single point down. Like this. Now if we apply the change inside the function or with the dependent value, then it will move to the left right position. If we decrease the function, the graph will shift to the right. Now we have another vertex. Vertex basically means the origin of the graph. For xy plane, the vertex is here, and for parabolas, the first vertex is here, but the second one is here. Similarly, when we apply there was decrease here, and then we can apply an increase, the graph will move to the left side of the plane like this. Now there are going to be stretches. Stretches are being applied when the function is multiplied with a scalar quantity. Let's take that scalar quantity as 3. If the scalar quantity is positive, then it will be stretching vertically like this. This won't be changing the vertex of the parabola. It will just create a space of 3 points here. Similarly, if it compress, if we multiply the function with a negative signed scalar, it will be compressed 3 times of the function. Now on to the last example. If you apply negative sign on the original function, the function will flip upside down, like you see a reflection in a pond or still water. That will be it. Similarly, if we apply a negative sign inside a function, it will flip from left to right or right to left. Since we know that if we use the same example as before, it won't be giving the same result. The reason is that if we apply a negative sign inside the function, which is a quadratic function, the function will itself become the same. Since it's an even function, we're going to use an odd function where the power is odd to clarify that example. So quadratic, it's not a quadratic function, it's a cubic function. The cubic function is drawn like that. It's actually a piecewise function. Piecewise function are that are not continuous. It breaks from here. So when I apply a negative sign inside the function, which will give something like that, the function will become flipped, but on to the sideways, not upside down. That's how it's going to be drawn. I hope it's clear to you. So when there's a question about shift or transformation, you're getting confused or try to draw the whole graph, you can just by guess it using these shortcuts. Now we have another example, another form of polynomial functions, which is the polynomial function. So since we already studied what a polynomial is, there are a few types of polynomial. First are linear. Since we already studied what a linear function is, so a linear function is basically written as y is equal to mx plus c, where x can be coefficient with a 1 or it can have a 0 constant. So this is a linear function which will give a straight line graph. Here m is slope. So if we want to find the slope of a function, we can always make that function, make that equation into this form, and we can take the coefficient of x as a slope. But if we don't have an equation, we are given 2 points, we can use this formula here to find the slope. So slope is basically as it's shown in the expression, that it is a slope created by the function. This is the slope. It has a run, which can be sometimes called a rise, and it has a fall. You can say this is the rise and this is the fall. Now we have X-intercept and Y-intercept as shown in the definition here. X-intercept and Y-intercept is basically the line that crosses the y-axis, and X-intercept is a line that crosses x-axis. For these two situations here, we have an opposite result. Like for y-intercept, x is basically 0. So in an equation where there exists an y-intercept, you can put x as equal to 0 to find the y-intercept. Here, this line here is the x-intercept, and this one here is the y-intercept. For this one here, x is not equal to 0, yet y is equal to 0. Similarly here, x is equal to 0 but y is not equal to 0. Now move on to the next concept, which is about parallel and perpendicular lines. To find the parallel and perpendicular lines, we have to study their slopes. This is the easiest way. If there are two equations, and we have to show that the line intersecting them is whether parallel or perpendicular to each other, we can always use their slopes. For example, this is the slope of the first equation and this is the slope of second equation. And to draw the lines, this is the first line and this is the second line. So you can basically see that these two lines are parallel to each other. But to find out that if these are parallel or not, we can find their slopes for line 1 and slope for line 2. If they are equal to each other, then that means that those two lines are parallel to each other. But if the reciprocal of the slope is equal to the -1, then these are perpendicular to each other. These are the formula that makes the question easiest to find out whether the lines are parallel or perpendicular to each other without solving the whole question or without drawing or graphing the function. Next we have quadratic function. Quadratic means the highest degree of a function is 2. So as I told you before that a quadratic function graphs a parabola. A parabola I've shown you before. It's an oval-like shape. So a parabola can be of various types. A parabola can be open up to the left of the graph, to the right, to the up, or to the downside of the graph. To find out that, we have basically the direction of parabola according to the coefficient of x square. If a here is positive, the parabola will open up, and if the a here is negative, then the parabola will open downwards. Now we have to a formula to find the vertex. I told you what a vertex is. Vertex can also call the origin, and for x and y graph, the origin is basically the line intersecting those 2 points. Here, this point here is the origin or vertex of a function of graph. Next we have axis of symmetry. So the axis of symmetry is basically the line that passes through the vertex. If this is the vertex, then the line of symmetry is x-axis. Then we have an X-intercept, already studied that. Y-intercept, already studied those two. And vertex form. If the vertex is not on the mid of the plane like this, if it's not here, then we have to find that exact position by applying this formula here, where h and k is a new vertex which is not in the middle of the plane. So for example, if you get an example which is find the maximum value of function which is minus x square plus 4x plus 2. We're going to apply the formula above. Here a is equal to minus 1. This shows that a is negative and the parabola opens downward. When the parabola opens downward, this means that the value is going to be maximum. To find that maximum value, we have the formula here which is called xv is equal to minus b over 2a. b is the coefficient of x and a is the coefficient of x square. Here the answer is 2, and 2 is the maximum value of the function. Now move on to the higher degree polynomials. A degree with the power even, and so on. Similarly, for odd we have x power 3, x power 5, x power 7, and so on. But if the degree of the polynomial is a1, it means that the both ends of the graph will go the same way. If they're going to up, then they're going up, and if the other single one is going down, the other was going to down too. Similarly, if the degree is odd, the ends will go up going in the opposite directions. The one is going right, the other is going to go left. Like the one we studied with x power 3, is it basically like this. It had a breaking point and it had a different endpoints going in the different direction. There is a function which have a factor in the form of this. Then if the multiplicity of that function is odd, then that graph will cross x-axis, and if the multiplicity is a1, then the graph will touch any axis and it will bounce back like in a parabola. Now how many turning points of the polynomial we have in a graph? It basically depends upon the degree of polynomial. So what's a turning point? Turning point basically means the peak value of the function when we apply a vertex of a maximum parabola. So it will have n minus 1 turning points. It can be used in a formula or in an MCQs directly. There are many MCQs relating higher degree polynomials. We're just studying it for the basic concepts. Then we are going up to rational functions. Rational is basically functions that have a fraction, a numerator and a denominator. The most vital skill for IMAT here is finding asymptotes. Asymptotes are basically the lines in a graph that gets incredibly close to each other but never touches. Like here we have a vertical asymptote. These lines here are very close and they will go up to the infinite direction of the graph, but they will never touch each other. They will get incredibly close but they will never touch each other. Then there are two asymptotes. Then there is vertical asymptote and the horizontal asymptote. So vertical asymptotes are the asymptotes that occur when a rational function denominator is equal to 0. This will cause the output to blow up toward negative infinity and positive infinity. To find the vertical asymptote, you need to simplify the fraction completely. If the value of x still makes the denominator 0, that line x, you can call it x, is a vertical asymptote. Then we have horizontal asymptote. So horizontal asymptotes describes that what happens to the graph when x becomes a massive positive or a negative number. So we can find it by comparing degrees of p and q. We're going to study that comparison in the next slide. Oblique asymptote is basically the situation in horizontal asymptote. We're going to study it later by doing the comparison of the degrees of p and q. Then we have a whole. So when a factor cancels out from both numerator and denominator, from both p and q, from numerator and denominator, it creates a whole, a single missing point, rather than a vertical asymptote. So it's basically not an asymptote. Now we're going to find the horizontal asymptote by comparing the degree of p and q, by comparing the degree of numerator and denominator. Let's say that the top degree is less than the bottom degree. So in this scenario, the bottom grows much faster and the y becomes equal to 0, or basically the x-axis. This will give the horizontal asymptote, which is going to be y is equal to 0. For example, here 1 over x square will become y equal to 0. Now when the top degree or the top value of the fraction becomes equal to the bottom degree, then to find that horizontal asymptote, we have the formula, which is equal to the leading coefficient of numerator divided by the leading coefficient of denominator. For example, here the leading coefficient of numerator is 3 and here the leading coefficient of denominator is 1. So 3 divides 1 equals 3. Lastly, when the top degree is greater than the bottom degree, then there won't be any asymptote. Because that the top grows so fast that it doesn't make the same output like of vertical or a general horizontal asymptote. So the graph goes to infinity or has a slant or oblique asymptote. This here becomes oblique. Now on to our last topic, which is an exponential function. Exponential function basically means the function has a power or a degree in the form of a variable. It can be written in form of this or like this. Here A is the Euler's constant, which has the value that goes on like this. Just like the general quadratic function makes a parabola, an exponential function makes a steep graph that rapidly rises or drops. It's because of the presence of an exponent. Since the exponent has a dependent variable which is x, it will cause the power to become rapidly fast, rapidly greater. So the value will become something like, it will go something like this, or sometimes it will go suddenly down. So this rapid decrease or rapid increase in the slope of the equation is due to that there is a dependent variable in the power. We basically draws the whole graph by changing the value of x. If x is 1, then there is 2. If x is 2, then it will jump twice. If it's 3, then it will jump 4 times. That rapid increase or decrease in the values cause this slope. The other concepts of domain and range, x and y intercept, and horizontal asymptote are basically the same. The only thing you need to memorize about this point here is that the slope is look like this, and there is going to be a rapid increase or decrease in the slope. It's because of the presence of variable here. That's all for today. We're going to study the other parts of today's lecture in the next time. Until then, study hard.